Welcome to The Explainer. Today, we're diving into a real mystery, a classic algebraic identity crisis pulled straight from the CSIR-NET/JRF mathematics exam. We've got our hands on a very specific matrix, and our mission is to figure out its true mathematical nature by looking at how it behaves under pressure. Basically, we're going to put this matrix to the test, analyze its core properties, and figure out exactly what kind of matrix it really is. Let's get right into the math.
Meet our prime suspect, matrix A. It's a 3x3 square matrix packed with integers. Across the top row, we have 2, -2, and -4. The middle row is -1, 3, and 4. And rounding it out on the bottom, we've got 1, -2, and -3. Now, the exam gives us a multiple-choice challenge to classify this exact matrix. We've got 4 possible identities to choose from. Is it nilpotent? Is it involutory? Is it idempotent? Or is it none of the above?
Okay, so what do these terms actually mean? Let's break down our suspects, starting with the nilpotent matrix. A square matrix is nilpotent if, when you raise it to some integer power n, the whole thing just collapses into a zero matrix. It literally multiplies itself into nothingness. For example, strictly triangular matrices, where everything on and below the main diagonal is a zero, are classic nilpotent matrices. Give them enough time, and they'll eventually wipe out all their non-zero entries. Next up, we have the involutory matrix. You can think of an involutory matrix kind of like a mirror. A square matrix gets this title if multiplying it by itself, calculating A squared, gives you I, the identity matrix. That's the one with the ones running down the main diagonal and zeros everywhere else. A really great geometric way to picture this is a reflection. If you reflect a point across a line and then reflect it a second time across that exact same line, you're right back where you started. Applying the operation twice gets you back to the identity. And bringing up the rear is our final profile, the impotent matrix. A matrix is impotent if A squared simply equals A. This one is stubborn. It refuses to change. Geometrically, these act like projection operators. Think about it. If you project a three-dimensional object onto a flat two-dimensional plane, what happens if you try to project it a second time? Absolutely nothing. It's already flat on the plane. Applying the operation twice gives you the exact same result as applying it once, so A squared equals A. Now, you might be noticing a pattern here. All 3 of these definitive properties, nilpotent, involutory, and idempotent, hinge completely on what happens when you raise the matrix to a power. So our game plan is actually pretty simple. The most logical first step for our investigation is just to calculate A squared. If it turns into the identity matrix, it's involutory. If it stays exactly the same, it's idempotent. And if it starts collapsing toward a zero matrix, well, we might be dealing with a nilpotent matrix. Finding A squared is the ultimate test. All right, let's roll up our sleeves and look at the setup. To find A squared, we're going to place matrix A right next to a carbon copy of itself. From there, it's just standard matrix multiplication, taking the dot products of the rows from the first matrix and matching them against the columns of the second. Finally, we'll simplify all those integers. Honestly, in high-pressure exams like the CSIR-NET, understanding the concept isn't the hardest part. The real challenge is dodging those silly arithmetic mistakes when you're under the clock. Let's walk through it together. Let's look under the hood at the raw mechanics here. Take the dot product for that top left cell, for instance. We multiply the first row of A, 2, -2, -4, against the first column of A, 2, -1, 1. So 2 times 2 gives us 4. -2 times -1 gives us a positive 2. And -4 times 1 is -4. Combine all those and we get 4 plus 2 minus 4 for that very first position. We just systematically sweep rows against columns like this for all 9 positions. I highly encourage you to try and mentally verify the arithmetic as we go. Let's crunch those numbers and reveal the final result. In that top left corner, 4 plus 2 is 6, minus 4 brings us right back to 2. For the top middle, -4 minus 6 is -10, plus 8 gives us -2. As we clear the dust and finish the basic addition and subtraction for every single spot, a beautifully crisp 3x3 matrix emerges. Just take a really close look at these final numbers. 2, -2, -4 right across the top. Wait a second. Do these numbers seem familiar to you? Boom, here is our aha moment. On one side, we have our original matrix A, exactly as we were given it at the start. On the other side, we have our newly calculated matrix A squared. Just look at row 1. Look at row 2. Look at row 3. No way. They are an absolute perfect match. We literally multiplied the matrix by itself, did all of that arithmetic heavy lifting, and somehow wound up exactly where we started. So, what does this all mean? because our calculated matrix perfectly matches our original matrix, down to the very last integer and negative sign, the mathematical equation a squared equals a is undeniably true for this specific matrix. The algebraic evidence is absolutely crystal clear.
And that brings us to the verdict. Because a squared equals a, we can officially classify this matrix as a geometric projection operator. We are confidently locking in option C, idempotent. We've successfully cracked the CSIR-NET/JRF problem just by rigorously applying the core definitions to our calculated arithmetic test. Before we wrap up this explainer, I want to leave you with a bit of a brain teaser. We just proved this matrix was idempotent. But what about the involutory option we talked about earlier, where a squared equals the identity matrix? If we were to change the trace of our original matrix or manipulate its eigenvalues, how would that fundamentally shift its identity? I challenge you to grab some scratch paper, tweak the entries of matrix A, and see if you can intentionally construct an involutory matrix of your very own. It's a fantastic way to reverse engineer these properties. Keep exploring the algebra, and I'll catch you in the next explainer.